designs. Another type of design that is often used, and I myself have used it several times, is that of tailored baselines. Now, the idea is that instead of comparing task A and task B to the same common baseline, you'd compare task A to its own baseline, so to control task A, and you would compare task B to its own baseline, which is control task B. The idea is that each control task is tailored to remove some kind of type-specific component, to remove some kind of task-specific component from your task of interest. Let me show you what I mean. And this is from a paper I published a few years ago. As a context, I was interested in understanding whether the parts of the brain that allow you to understand the relationships within natural language are the same as the parts of the brain that are needed to understand other type of relationships. For example, the relationships of algebra. Allow me to make you my participant for just a second. Okay, so you might be inside the MRI machine, and I would present you with this pair of sentences, and the task of interest, so task A, is read the two sentences and tell me if they match. Do they mean the same thing? Do they imply the same state of affairs? Do these two sentences refer to the same state of the world? So let's try the first one. Z was paid X by Y. It was X that Y paid Z. Can you transform one into the other? Do they mean the same? Do they imply the same state of affairs? And the answer, of course, is yeah, absolutely. And you can shuffle things around so that sometimes the two sentences don't match. And remember, your job is to tell me, do they match? Do they not match? Now, this is task A. Task B was essentially the exact same task, but the stimuli were different. The stimuli were algebraic in nature instead of linguistic. So, for example, a stimulus might look like this. X minus Y is greater than Z. Is that the same as Z plus Y is smaller than X? And again, your job is to tell me if the two states of affair match. And of course, with a simple bit of algebra, you will find out that the first and second statements can be transformed one into the other, so essentially mean the same thing. And just as for the linguistic inferences, if you shuffle around X's and Y's, you can create statements that do not match in the same way. So whether it's linguistic stimuli or algebraic stimuli, your job is to read the two sentences and tell me, do they mean the same? And see, what I was interested in is to understand when you're doing the thinking and you're manipulating linguistic relationships versus manipulating algebraic relationships, is it the same parts of the brain that understand and manipulate these relationships? And this goes back to a very general question of whether language is important for other aspects of human thought, such as algebraic reasoning. Now, however, if I were to look at the activations, let's say, during while you are reading these two sentences and trying to decide if they match or not only I'm getting the parts of the brain that are important for you to think about whether the two sentences match or not, but I'm also getting all the parts of the brain important for vision, because you have to read the stimuli. I'll get the parts of the brain important for recognizing and decoding words, and I will get parts of the brain that will transform words into meanings, et cetera, et cetera. I want to get rid of all of that. I only care about whether, for thinking about these relationships and manipulating them, that's the cognitive process that I care about. So we picked a baseline a baseline task that would subtract everything. And so the baseline task was as follows. We would show the exact same pairs again. We randomized the allocation of X, Y, and Z, but other than that, it was the exact same sentences. But this time, you are told as a participant, don't bother on whether they match or not. Just tell me, are they both grammatical or not? Or is either incorrect? So I would show these same sentences to you a second time, of course, randomized and at a distance in time. And your job this time is to just read them and tell me, are they both grammatical or not? And of course, you will notice that in order for you to decide whether the two sentences mean the same or not, they have to be grammatical. They cannot be ungrammatical. So every now and then we put in some fake arguments, some fake pairs that are only meant to distract you so that you could say that these were ungrammatical. To give you an example, 2x was made by z for y. That doesn't quite jive. Same as y equals z times greater than x. That also doesn't match. So you, as the participant, when you're doing the grammar task, you read this and you go like, oh, that doesn't seem right. And you'd say, they're not both incorrect. They're not both grammatical. And then you would read this and you would say, I don't know, there's something wrong with that one. Okay. And of course, I will never look at the brain activations during these catch trials. They're just meant to keep my participants honest. What I want to do in order to address my question is to do a subtraction. So I will take the brain activations while you are reading these sentences in order to decide whether they mean the same or not, which we call inference. I will subtract to that its own baseline task, which is reading the exact same sentences just to decide if they're both grammatical or not. And ideally, when I do this inference, the activations during the inference minus the activations during reading, ideally what's left is what you need in order to process the stimuli and decide if they match or not. So I've isolated this way you manipulating and processing linguistic relationships. So task A, which is inference, has its own baseline, which is reading the same sentences for grammaticality. Now task B, which is the inference with the algebraic sentences, has its own baseline, which is reading the algebraic sentences just to tell me if the two sentences are both grammatical or not. And if you think of it, you really want to have a tailored baseline because it would make no sense to use as a baseline for the algebraic inference. It would make no sense to use the linguistic sentences. You would not be subtracting off the same thing. So for inference, for the linguistic type inference, I want to have linguistic type baseline. And for the algebraic inferences, I want to have algebraic type baseline. And then I would subtract reading these sentences from thinking about them, which is what you see here, inference minus reading for the linguistic stimuli. And then I would compare that to the parts of the brain that are active when you subtract reading the algebraic inferences here from performing algebraic inferences. And then, of course, the question I cared about was, is what remains, is what you use to think about these two problems the same or not? And in particular, does it engage a certain part of the brain? But see, what's so crucial here is that each task requires its own baseline. It would make no sense to have a common baseline. Now, of course, this task also has its own assumptions. For example, it assumes that each baseline removes the same amount of task-specific processes from its task of interest. So it assumes that control task A removes the same sort of task-specific components from task A, the same way that control task B removes, task-specific stuff from task B. It also assumes, again, that both the tasks and the baselines have similar psychometric properties. Now, here, it would be a good idea to have a common baseline just to try to address the question of whether the two tasks are similar or not. And in particular, it's a very good idea to compare the two baselines. So for example, I might also want to do control task A versus control task B, just to get an understanding of whether these two are similar enough or whether they're very different. Now, a different design is known as hierarchical design. Now, the idea here is to use not just one task, but a set of tasks, each of which sits at a different level within some kind of cognitive process, within some kind of hierarchy, rather, of cognitive processes. Let me show you an example from a real paper published in 2005 by Jenny Rod and colleagues. Now, they had three tasks, and it went like this. Task A was just to listen to noise stimuli. Task B would be to listen to sentences. And then task C would be to listen to sentences that contained in them ambiguity. And so they had these three different tasks, and you'll notice that each task, in a sense, is a little higher in the cognitive hierarchy of processing sounds and turning them into meanings. So what they did is they first compared noise versus just silence. And this shows you what parts of the brain are important for just processing sound. And it turns out to be these green areas, which you will have noticed are in the superior temporal gyrus. Now, then you take one step above and you say, okay, so on top of just listening to sounds, what is it about listening to sentences compared to sounds? In other words, what is special about listening to listening to sounds that have a certain organization to them compared to just listening to sounds that don't organize into anything, right? So just noise versus sounds that are sentences. So notice that all that we're looking at is what is special about this additional step compared to the step before. And so you might look into the brain and you'll find that all these blue areas are more active, are active when you look at sentences above and beyond what you need for noise. And finally, you might say, okay, but let's take one more step. What is special about listening to ambiguous sentences compared to non-ambiguous sentences? It turns out there's some part of the brain here portrayed in red that is important for listening to that is important for resolving semantic ambiguity. So the beauty of this design is that you can build one step on top of the other, your subtractions, and you can tell, okay, so here's what listening to noises compared to nothing. Here's what listening to sentences is compared to listening to noises. So when you add that extra step of listening to something that is meaningful, how does that change your brain activation with respect to just noise? And then if the meaningful thing on top of it has ambiguity in it, how does that change the activation in the brain compared to meanings that don't have ambiguity to them? Okay, so the beauty of this is they can sort of build through this cognitive hierarchy and try to understand what is special about each additional step in this cognitive hierarchy. Of course, you'll realize that now you're assuming that at every step you can insert an additional process without changing all the processes up to where you were. In other words, you're assuming that at every step, pure insertion must hold.